At the first virtual Ifac World Congress, all plenaries and semi-plenaries are accompanied by a specific live element. This presentation is followed by a live panel discussion, where experts in the field recapitulate and debate on related ideas, questions, and open problems.
Welcome. Thank you very much, Professor Lee, for a very interesting plenary presentation at this Ifac World Congress. We're going to follow up now with a live panel discussion, an online panel discussion on industrial potential of reinforcement learning. Of course, a very attractive topic. We have 4 panelists, and of course, Professor Lee also involved. My name is Paul van den Hof. I'm a full professor in Eindhoven University of Technology, the Control Systems Group. And my domain of expertise is typically related to data-driven modeling, model-based control in all kind of application areas, among which process control and all reservoir engineering. And lately, I've been focusing back again on data-driven modeling issues, particularly in dynamic networks. I will be moderating this live panel discussion, but first I would like to introduce the panelists to you. We have first Thomas Batchwell, Advanced Research Associate at ExxonMobil. Tom received his bachelor's degree from Rice University and master's and PhD degrees from the University of Texas at Austin, all in chemical engineering. He held positions at SetPoint, Fisher-Rosemount, Rice University, and Aspen Technology prior to joining ExxonMobil in 2009. At ExxonMobil, he focuses on development and applications of advanced process control, in particular model predictive control and deep reinforcement learning. So you could say right on top of the subject of this session. He received the Computing Practice Award from the AICHE Computing and Systems Technology Division in 2013. Secondly, we have Dr. Alf Isaacson, Corporate Research Fellow at ABB. Alf has a PhD from Linköping University from 1988. Then he moved to KTH Stockholm and he joined ABB Corporate Research in 2001. From 2012 to 2019, he was coordinating all control research at ABB and is since recently Corporate Research Fellow for Automation and Control. Alf is a member of the Ifac Industry Committee and of the Swedish Royal Academy of Engineering Sciences. Our third guest is Dr. Joseph Liu, Chief Scientist and Senior Fellow at Honeywell. And Joseph joined Honeywell after receiving a PhD from the University of Washington in 1990, played a key role in the development of 3 Honeywell MPC-related products for unit-wide and/or refinery-wide closed-loop optimization. He's the recipient of the 2010 Control Engineering Practice Award from A²C². And finally, Professor James Rawlings. He's a professor at the University of California in Santa Barbara. Jim is the Mellenchamp Process Control Chair in the Department of Chemical Engineering at UCSB. His research interests are in the areas of chemical process modeling, monitoring and control, nonlinear model predictive control, moving horizon state estimation, and molecular scale chemical reaction engineering. He's a member of the US National Academy of Engineering and a fellow of Ifac, IEEE, and AICHE. So that completes my panel. Welcome, all of you, and great that you are participating in this session. I would like to kick off the discussion addressing a question to Tom as the first speaker. Tom, we've just seen the plenary of Jay, and I was wondering, and I can bet that maybe many people in the audience are also wondering about this, is a machinery that can beat the world champion in Go also suitable for controlling your chemical plant or nuclear reactor? What would you say to that? Tom, the floor is yours.
Well, that's a loaded question, of course. Let me first thank Professor Lee for giving us a great presentation. And let me thank Professor Lee and the conference organizers for putting together this panel and inviting me to participate. So can we use those tools for process control? It depends kind of on what you mean by process control. And let me explain what I mean by that. I think that if your idea is to replace PID controllers or model predictive control with deep reinforcement learning, then as Jay said in his presentation, I believe that's probably not going to work very well. One of the real issues with deep reinforcement learning is how much time it takes to train the agents. So you have a particular control problem, you may need millions of encounters with the environment to train the agent. Now, if you look in my world, a typical model predictive control application, say it runs once a minute, it may have 20 different actions, it may have 50 states that you're trying to control in some way or another. And at every minute, the operator may select a subset of the actions in the states to control, and the operator may change the reward function to speed up or slow down the control. And you need that flexibility. You absolutely have to have it. That means that you would need to train an agent on all of those different possible environments in order for it to work effectively. You have to anticipate every possibility and train the agent to do that. And that's just not feasible at all. So what we've been doing, and we've been looking at reinforcement learning for a number of years now, we're thinking about other applications. What are some of the things that you do in the control room to manage control systems, for example? Say tuning controllers, responding to large-scale disturbances like a rainstorm. When these things happen, there are certain things that the operators do to the control system to manage it. They may add a little more heat to the bottom of the distillation columns if it's raining. They may do other things. And we think that an agent can learn some of those things and maybe help to alleviate some of the tedious, repetitive things that you do in a control room. But to think that you can go in and replace the current set of tools, which have been optimized for what they do over 30 years now, is not realistic.
Okay, thank you. Jay, does that give you a reason for responding?
I agree with him completely. I don't think, already I think process industry is highly automated with a lot of good tools like PID controllers and model predictive controllers. I think, but it does have a place in certain types of applications where these techniques are not entirely effective. And I think it's up to industrial people to maybe rediscover reinforcement learning in some applications context, as was done with MPC.
Okay, let's move to Alf. Alf, how do you perceive these developments on RL from, let's say, from your position in ABB perspective?
Thank you very much, Paul. And thank you, Jay, for a very nice presentation, and for Jay and the organizers to invite me to this panel. I mean, my main comment is with respect to modeling. You may not have said it explicitly, but I get the impression that we really want to look at training the reinforcement learning on a simulated model. So there is an underlying assumption on access to a process model. And that's not a small assumption. It may be more valid in mechanical systems, and for robots, we see reinforcement learning being applied. But as we know, for chemical processes, first principle models are not readily available. So, and for us, engineering effort is really a key. We need to cut down for every year on the amount of time it takes to commission a controller. And that would be my concern here. We were already, jokingly saying that we struggle to make the commissioning PhD free. So yeah, this is where I see the biggest hurdle, even for conventional MPC.
How do you, is clear your response, Alf, the importance of the underlying modeling phenomena? How do you see that in this development towards RL type of techniques? So what do you think that the development of MPC-like control systems should be in order to address that issue that you just mentioned?
Thank you very much. I see that we go in, of course, in the direction of using learning for process control. But maybe it's my training as a specialist in system identification in my PhD once upon a time. I kind of like the idea of estimating a process model. Some colleagues at ABB looked at an MPC scheme where you optimize and the model is a recurrent neural network. They presented it at the ECC last year. There is another follow-up presentation at this Congress where my colleague Mehmet Merchangus presents ways of making neural network system identification more autonomous. And to me, that's somewhat more appealing for the more traditional control problems. I think, as Jay said towards the end of the presentation, discussed more higher up in the automation pyramid. I think reinforcement learning can be really useful when we go up towards planning and scheduling and those kinds of applications.
Okay, thank you, Alf. So I basically, let's say, I'm collecting now the issues for further discussion already. I noted, let's say, what kind of applications should we be looking at for RL, and the process modeling and the desire for doing the process modeling is one of the other topics. We might pick up on that. We move to Joseph and see what his input is as a starting input for this discussion.
Well, first of all, thank you, Jay, Professor Lee, for your very interesting presentation. And thank you for, and also the organizing committee for inviting me to be on this panel for discussion. Perhaps I'd like to bring up a question for discussion from a vendor's perspective. Maybe, my question would have a little bit the vendor bent to it. If that turns out to be the case, so my apologies in advance. So in the last couple of years, the cases that we have come across in terms of, AI, machine learning / reinforcement learning have been the point solutions, or what I call point solutions, that are specifically designed for solving specific problems. The target application areas are typically in the space where the current approach either cannot solve well or can solve but not cost effectively. So, the example that the Tom Badgewell just brought up is a very good one. As you probably know, point solutions are typically lacks economy of scale, and its high cost would typically disqualify many similar applications that would have lower financial returns, right? So as a vendor of control solutions, our challenge is then to find a way to progress from point solutions to a more general purpose platform solutions in order to increase its addressable application space, right? A good example of platform solution, which we are all familiar with, is the MPC solution, right? Which can be applied without modification to a large class of applications in multiple industries. So one of the challenges in building a platform solution, I think, is a level of solution robustness required. So far, for the point solutions we have, it appears to be a little bit difficult to port or translate the experience or knowledge we learned from one application to another. Part of the reason, I guess, is in fact that our point solutions are not robust enough. A deeper reason, however, I think it is perhaps we don't have a sufficient understanding of our design choice, understanding of robustness impact of our design choices, right? For example, when we change the model structure or change the reward functions and so on and so forth, what kind of impact those choices may have on my overall solution robustness. If we use MPC platform solutions as a reference point, in the process of building an MPC platform solution, 30 years ago or 20 years ago, we benefited a lot from the robustness control theory. Not that we use the robust control directly, but for many MPC design choices, we did analyze their potential impact on robustness and try balance between the control performance and the robustness with the design choices we had at the time, right? So in order to build a good RL platform solution, I'd like to think it would be equally helpful if we can have a good understanding of robustness impact of my design choices. So I'm wondering if other panelists may have a similar or maybe different experience than mine.
Thank you, Joseph. From point solutions to platforms and robustness, I took up as two key issues. Maybe Jay can respond to the robustness issue, of which I'm sure you have been thinking about. And that may be also a point, I think, that pops up in several questions that are coming in from the audience on your plenary talk. How about robustness and how about guarantees? Could you expand a bit on that, Jay?
Well, as far as my knowledge goes, I don't think there could be any guarantee when it comes to reality, right? But the traditional techniques usually assume some sort of model of uncertainty, mathematical form, either, as I said, or probability distributions or something. Reinforcement learning is learning based on data, either online or offline. So the uncertainty must be expressed through this sort of simulations, or from, it comes from reality, right? So that's a little bit different. And I think while it doesn't offer guarantee like the robust stability and so on in classical sense, it does offer a lot of flexibility in terms of what kind of uncertainty you will consider in designing your controller. There are many different kinds of things that may vary or you cannot anticipate and so on, which may be very difficult to express mathematically, but still can incorporate into simulation, for example, and generate data which will which can be incorporated into reinforcement learning design. So yeah, I mean, while mathematical guarantee, I don't think is possible, it does offer something that's very practical in the sense that it gives you a lot of flexibility in considering all types of different kinds of uncertainties.
Okay, thank you, Jay. Let's move to Jim. Jim, moving from an MPC platform to a reinforcement learning platform. You've been spending tremendous amount of effort and time in developing MPC and working in MPC. Are you willing to give up your MPC platform for an RL platform?
Okay, thank you, Paul, for that very innocent question. I'm interested in insight and learning about new technologies. So I have an open mind. I think rather than making a general statement about what I think might happen, which might be useful, but rather than do that, let me ask Jay a couple of specific questions based on what he showed us, which I found very stimulating. So Jay, in your semi-batch polymerization, for example, you did some great applications, and I think the applications are probably going to teach us a lot. So in your semi-batch polymerization, you showed that certain choices, I think the actor-critic without breaking the problem into separate phases, did not work. And thank you for showing that, because we often see enthusiasts for a new technology showing us only the success stories. And I think that's important. You have to generate visibility and enthusiasm for new ideas. But if that's all we ever see, then we can be misled into thinking that the success is typical or almost guaranteed, and failures are rare. So I think the failures often teach us a lot more than do the successes. So my question is about insight. Why did that semi-batch problem defy the simple brute force approach? Why did it require careful engineering of several different approaches working together? And what lesson do we learn from, say, that example, the semi-batch polymerization? And secondly, in the application for energy planning, which I found very highly interesting, why did you make these many engineering decisions and judgments that you made during that project? For example, why did you invest so much effort in the wind model? You had a Markov model, you had to choose an order, you had to estimate parameter values, etc. Why, what would have happened, or why did you, maybe you thought about it, maybe you tried it, why not just stick all of the wind data into a neural network and train the network? We have a lot of wind data, why not just train the network to make that forecast and do very little engineering on the decisions and the model structure? So if you could share with us some insight into how you made some of these complex applications, how you brought all these technologies together, I think that would maybe tell us a lot about what might happen next, or what the appropriate places are for MPC versus reinforcement learning and so forth.
Jay?
Okay, well, polymerization, semi-batch reactor. The reason why I think it may be a good target application is because, first of all, it represents the nonlinear control problem with significant stochastic uncertainty, especially initial uncertainty. And I know that industrially there are efforts to develop very, very detailed fundamental first principle models. So the reason why they do that is because they make these polymers and they want to make sure that they hit consistent targets and so on. So I know companies are into developing this sort of model. So I thought that would be a good target. Why did I choose things like phase segmentation and Monte Carlo as opposed to temporal difference? Well, I tried them and they failed. And then I analyzed the failure and thought that, yeah, temporal difference is based on bootstrapping. So if you don't have a good estimate to begin with, then things just go bad. And also when there are sharp transitions, like in semi-batch operations, then the single neural network is very difficult to train. So, generally speaking, there's a lot to do in terms of engineering in making this reinforcement learning work. For example, one of the great advantages of using model predictive control is that the fact that you can address constraints. But, mostly, at least state constraints, they have to be imposed as soft constraints because you don't want to have infeasibility online, right? But what happens is that when you include these soft constraints in the reward function, the value function becomes very non-smooth. So it's very difficult to train, and the training can fail and so on. So, what we found is you need some sort of a parameter evolution as you would do in interior point method, for example, as you train and have to go sharper and sharper in terms of this value function estimates. So, this just comes from experience. And what I find is that making this sort of technology work for particular application is not that simple. So you have to kind of try and then see why they failed. As you said, you learn a lot from failure, and then you say, okay, what can you do to overcome these problems, right? So that's how we arrived. There's no systematic kind of framework or methodology to go at it. There are all sorts of different algorithms and tweaks you can make and so on. And I'm sure that's probably was the same for MPC in early days as well, right? In terms of the other question, why did we spend so much time developing wind model? Because that was kind of the key, to be able to forecast these wind variations long enough. For example, we had this daily unit commitment problem. And to take advantage of these decisions, you had to have a good forecast into what the wind will do next day. And then we had this hierarchy of decisions at multiple timescales. So it wasn't enough to just be able to predict. We had to do this at multiple scales and in a very consistent manner. So because it was important, because we had to make decisions in multi-scale, that we created this wind model hour to hour, day to day, month to month, in a very consistent way. Did that answer?
Yes,
your question?
great.
Any of the other panelists that would like to respond? One of the points that you mentioned is that it will be tough to do, let's say, constraint handling in a similar way as we are doing it in an MPC environment. I mean, how tough is that to accept for people from industry? Tom, Alf, Joseph? How strong do you adhere to your constraint handling?
Sure, yeah, I'll be happy to try to address that question. How important are constraints in our applications? Arguably the most important thing about MPC for us is the ability to handle constraints and to consistently push our units up against the constraints to maximize profit, maximize feed rate, and so on. So yes, it's difficult to get RL to respect constraints. That's something that we noticed pretty quickly, and that's something that's very valuable about MPC.
Okay.
Yeah, I would agree that constraint handling typically is set at a higher priority than optimization. If a solution would not be able to protect the constraints very well, the chances are that the operators are going to turn it off very quickly. So now, if the RL solutions right now having a little bit difficulty to handle the constraints, maybe we can add a little bit buffer in, within the solution set, so that the solution set need to be looking at more constrained space to find a solution. And even if we violate a little bit, to the outside operators, it may not be a violation to them. So that might be a way to quickly get a better acceptance early on before we address the constraint handling problem more rigorously.
Let me just clarify what I said. I said it's difficult. It's an issue that needs to be looked at, maybe more rigorously from research perspective, but it's not an inherent problem, I don't think. It's an optimal control, just as MPC is, and there are ways of doing this, I'm sure, in very rigorous way, and algorithmically sound way. But we just need to be careful. I mean, it's an issue right now, but I don't think it's an issue that cannot be overcome.
Okay, thank you. So one of the points that I would like to bring to the table is the element which is also present in your plenary, Jay, about, let's say, offline learning and online learning of dynamics or strategies. I mean, and one of the pictures that I have in my mind is a look at how MPC is being utilized in process industry is, let's say, once it's commissioned, it's running, but situation occurs that either the moment comes that operators don't understand what the MPC is doing, or the processes have changed, and the MPC controller is being switched to manual, and we don't have a really good technology yet to bring them live again, rather than redoing the full project. Looking at such a situation, and then considering offline or online learning, it seems that that situation that I described typically has to be addressed by online learning and not by offline learning, because typically things happen that you cannot predict up front. How would you deal with that? Or how would you like to comment on that one?
May I comment? I think you can do something online in a meta manner to have the reinforcement learning help you to know when it's time to remodel, or if you go one level up, to help you to know when you should reschedule, when you should find a new production plan. I mean, there have been attempts. I mean, one of my ABB colleagues here, Ironkoski, with a postdoc, looked in a paper recently on how to, I mean, on top of traditional scheduling, you determine whether you want to redo the schedule. But to use reinforcement learning for adaptive control, yeah, I think we have quite a long way to go there.
I think the problem, Paul, you brought up is a very good one. This is a space where we could certainly benefit from the development of new tools. I think the industry has been working at it for a long time now, at least more than 20 years. We still don't have a very good automated adaptive tools that would upkeeping the APC solution running for a long time. The problem is not so much that the APC controller would degenerate over time. That happens to be, the general description. The problem really is the process is going to change over time. Is it because of a revamping? Is it because of the heat exchange is going to fall, or a lot of things is going to happen over time. Typically, over a year or two, well, typically over 2 or 3 years, there will be enough change in the process that would cause the controller, or at least some portion of the controller, would the performance would become degenerated. So this provides an opportunity, I think, for the reinforcement learning type of tools, that if you could continue to learn online through the online data, at least if you could even warn the APC engineer that something needs to be taken care of, and in what direction, right? Which part of the model actually is degenerated or doesn't match with the real process. That would provide a tremendous amount of value to the industry, so that we can perform more targeted services rather than just looking at a whole big, 40 by 80 matrix and exam models and one by one. That's just too time consuming.
Tom, yeah. We were slightly running until the end of the session, so we don't have very much time left. But Tom, the floor is yours.
Yes. So regarding this question of offline learning, I think that's some place where there may be some very good potential for reinforcement learning techniques. There have been some articles recently. There was a review article by Sergey Levin at Berkeley on offline techniques. And we currently don't have any techniques to look at our large collection of closed loop offline data and extract anything useful out of it. So to be able to pull out an initial policy for a problem that we could then use to, in combination with MPC or to maybe guide our testing, I think that there's a lot of value there. Now, to go back to your specific scenario of the operator seeing something strange come out of the MPC and turning it off. In that case, I think you're in a much better situation when you have a process model that you can use to sort of back out what might be happening to the controlled variables that would cause the suggested changes. When you have a reinforcement learning agent, it's a black box. You don't know why the actions were taken. And so you really don't have much of a way to answer that operator's question of why did it do what it needed to do. And I know that's an active area right now in research, reinforcement learning research. But you are in a better position to answer those kinds of questions when you have a process model.
Yep. Thank you very much, Tom. We are moving to an end of this session, unfortunately, because there are also still very many questions left from the audience, but we cannot address them. I think it's a very challenging topic, a very stimulating topic, addressing the question how process control will move into this era of artificial intelligence, because I think that to some extent that's what we're talking about at this moment, and move to the next area where we use data in a way more effective way to control our processes. At this moment, I would like to thank you very much, panelists, for your contributions to the discussions. Jay, thank you very much for your plenary. This closes this session. Thanks for the audience for participating, and I wish everybody a very nice continuation of the Ifac World Congress. See you next time. Bye-bye.
Bye-bye.